right, 8.1, distribution of the sample mean. All right, so statistics such as the mean, or x bar, are random variables since their value varies from sample to sample. As such, they have probability distributions associated with them as well, just like our regular each individual sample. So we can be looking at the sample of the means with that is what this is saying. Okay, and so we want to focus on the shape, center, and spread of statistics such as x bar, the mean of our populations. Okay, all right, so sampling distribution is a probability distribution for all possible values of sample size n. Okay, now the sampling distribution of the sample mean, x bar, is the probability distribution of all the possible values of x bar, computed from a sample of size n, from a population with mean, mu, and standard deviation. So what that means is we're looking at a sample of the means. Okay, so we have a bunch of different means of size n from sample size n, and so we want to look what is the mean of that, what is the average of those things, what is the standard deviation of those means there on there. Okay, and so we want to look into those things. All right, so the idea here behind these, we have a few steps. One, we need a simple random sample of size n, compute the sample mean. And then we want to repeat that as many times possible until we have gotten all of the sample size n from our population that we could possibly get. Okay? And so once we get it obtained, also, if we have a sample, we can't do it again. So we don't ever want to repeat anything. All right. And so that would then allow us to break down that information and find out what we need. Okay. All right. So let's start looking here at these things and what all of this means. Okay. So here we have an IQ test, and the tests are approximately normal, so they have that bell shape to them. With a mean score of 100 and a standard deviation of 15. What is the sampling distribution of the sample mean for a sample of size 9? So we want to look at all of the size 9 samples and look at the sampling distribution for those means. Okay? All right, so if we let a computer generate all of these pieces, we would end up with a spreadsheet like this. Okay? And so we would see that we'd have a whole bunch of different means there, x bars, on those pieces. So you can see we got a whole bunch of them there, and that's not all of them listed for those. Now, once we go through and do all of that, and we kind of compile that, we end up with this bar graph over here that allows us to see what's going on. And we see through the bar graph that it is approximately normal. It looks very much like our bell shape, okay? And so we're able to utilize that and information and work with it. It gives us some good pieces to work with then, because then we can do things using the empirical rule and stuff like that if we know that it's close to normal, okay? Now, it does differ a bit when we're looking at these. Notice that the first one is the population. So when we're looking there, at those pieces, we want to compare what does the population and what does the samples look like. And so our first one over here is a little bit shorter, so it's only this tall compared to being up here. This one's a little bit steeper, so not as wide as this one over on this other side, okay, for those pieces. All right, so that's what we noticed there. So we see that the mean doesn't really change. Both of them still have a mean of about 100, but the standard deviation is what really changes the most there on those. It's at 5 compared to the population standard deviation of 15. Okay. Now, if we look at those pieces, the shape is approximately normal. The center is about the same as the population. But our standard deviation is much less than the standard deviation of the population. Okay. Now, if we increase the size of n, so we go from 9 to 25, then we see the same things. Okay, it still looks approximately normal. With those, the mean is still about the same, but that standard deviation, it's even gone lower with those. Okay, and so what does n do? N, as the sample size increases, the standard deviation decreases. Okay, and so all of that means that we can kind of go down to this formula. Now we need to make sure we pay attention to these. So the mean of x bar, or of the means, is still going to be the same as the mean of the population. So mu x bar is going to equal mu of the whole, and that's of the whole population. But our standard deviation here, that one's going to be a bit different, okay? So the standard deviation of our means, x bar, is going to be the standard deviation of the population divided by the square root of n being the number in our sample. Okay, so we always got to remember those pieces. Okay, so we want to make sure we have those formulas down. All right, now we can also call that sigma sub x bar there the standard error of the mean. All right. Now, if we have normal, we know it's normally distributed, then it's going to follow through with those pieces. Okay. So example here, going back to our IQ scores, we have n being 9, and we know that the mu of x bar is going to be 100, just like the mu of the population here. So we can see those two things. All right. And then the standard deviation here, the population is 15, and n is 9, and so that gives us that sigma sub x bar is 15 divided by the square root of 9. Now just pay attention to your homework. Do we need to leave it in that form, or do we need to find the decimal by plugging that in our calculator for those pieces? And we can, that's a pretty simple thing. 15 divided by the square root of 9, in this case, would be 5. Now they decided to leave it in the original form, but that's going to be, just pay attention in your homework there on what you need to do for that. Okay. So then we could change it as well here if we need to do size 10, and then work through that. We could figure out those pieces. Okay. And so using a size 10 for our sample size, we want to know what is the size of the results in a sample mean greater than 110, okay, with these. Now, we know it's normal, so that's going to help us with those pieces, okay? So if we kind of think back to previous section, then we can use that to our advantage, okay? And so in the previous section, we used the normal CDF, but in normal CDF, that is less than. So that means here, when we're looking at this, this tells me I need to do 1 minus probability of x bar being less than or equal to 110, okay, for those. All right, so we're going to use that piece to figure out what's going on there for those, okay? All right, and so when we do this, we need to do 1 minus, so we need to do second vars, and we're going to do number 2 there, normal CDF. Now, because it's completely less than, we're going to leave that negative 1e to the 99, okay? Now, I've already done this problem. I was practicing earlier, and so here we can see that our upper is 110, because that is our number, right? So we're looking at 110 there for that. Our mu, well, we know our mu is given to us. It's here. So we have our mu, so x bar is going to be 100. And then our sigma of x bar, well, that's going to be 15 over square root of 10. Now, we could do that decimal, but because we can type that right in, I went ahead and just typed it right in and let the calculator do the math for me. Okay? All right, and so then we would press enter. And so it should be here that the probability is 0.0175, or rounds accordingly. Okay? So let's see what they come up with. Here, now they do theirs by hand, and so again, they kind of work those pieces out on these. Now, we're definitely less than 5% of the population. We're looking to be greater than, okay? So they found their z-score because they're doing things by hand, and then found the area to the right. Now, it also says using technology down here, okay? For that is what we got, isn't it? So when we look over here, you can see I have that same result doing that. Okay. Now again, you could find your z-score of 211. We know it's to the right, so that's why we have the 1 minus. But if you go to your z table, you would find this score from your table over here, 0.9826. So we can always do that as well, just different ways. This other way allows the calculator to do some of those things for us. Okay. All right. And so then we could then interpret, this means that the probability of obtaining a sample with IQ greater than 110 from a population whose mean is 100 is approximately 0.2, because we rounded from the answers that we got there. Okay. All right, now, what if it's a not normal population? Okay, so if we were to take this information about the number in a household and what proportion of the population has that, we would see that our mu is 2.9 and our sigma is 1.48. Okay, and so this is what the graph would look like. Okay, and that is obviously not normal because it's not a bell curve. It's got a pretty good tail here at the end when we're looking at those pieces. So this is skewed to the right for those. Now, if we go and were to just work some of this out and let the computer do some things for us, we would see here that we get certain things. Okay, so for the first one, so they do different sizes of n. So n is 4 here on this example, and so they go through and calculate all those pieces, and we see that everything still matches the formulas that we had a moment ago using our sigma over n, our square root of n, and then also our mu being mu. Even if we did size 10, it would be very close, and as well for size 30 on those pieces. And so we can continue to use those same formulas even if it's not normal. All right? All right, so our key concepts here. So the mean of sampling distribution of the sample mean is equal to the mean of the underlying population, and it's still the standard deviation is sigma over square root of n, regardless the size of the sample. Okay, and we also see that as n increases, the more it looks like normal distribution on those. Okay, so the bigger our n gets, the more like normal distribution than it gets, which is always a good thing. And so that's what's called our central limit theorem. So regardless of the shape of our underlying population, as the sampling distribution of x bar becomes approximately normal as the sample size increases. Okay. All right, so here's just more of that same thing. We can see here as we increase our size on those pieces that it's going to get closer and closer to normal. So that's what all of that is talking about for us then. Okay. All right, so if the distribution of the population is unknown or not normal, then the distribution of the sample mean is approximately normal, provided that the sample size is greater than or equal to 30. So that's just kind of a way to look at that, okay? All right, so here we've got weight gain during pregnancy. So the mean weight gain is 30 pounds, standard deviation of 12.9. Weight gain during pregnancy is skewed right. So an obstetrician obtains a random size of 35 low-income patients and determines their mean weight during pregnancy was 36.2 pounds. Does this result suggest anything unusual? Okay, so first we look at our sizes. So we're looking at 700 low income pregnant women. Okay, and so kind of breaking down what all's happening in our original piece here. And so that's out of all of the even United States or even a state, that's a low percentage. So that's going to be less than 5%. So that says good. We can continue there of those pieces. Okay. And so the probability is represented over here. So we want to know what is that. All right, so we want to find the probability of x bar being greater than or equal to 36.2. Okay, and so we get 2.84 is our z-score. And so the area to the right is 0.0023 for those. Okay, and so if the population which the sample is drawn has a mean weight of 30 pounds, and the probability of a sample of 35 women has 36.2 pounds, that probability is approximately 0.002. And so that's pretty unusual, right? Because that's under 0.05 with those things. And so I would say that that is unusual to have that type of mean for those. Okay. All right. And so there are a couple of things we can also conclude from this. All right, so kind of wrapping up here is just what those formulas, but how the shapes differential. So if it is normal, then we know that we can talk about the things. We don't care what size n we have. We already know that it's going to fit our normal distribution. Now the formulas don't change for either one of those. But if our population is not normal, then as the sample size n increases, then the distribution becomes approximately normal with those. Okay. All right, so those are the things you're going to need here for 8.1.